in a hypothesis test, we want to know if the variables are related in the population, right? Again, we don't observe the population, but we know how tables from a population where there's no relationship look like, right? And we're going to compare our table to a distribution of tables where that are coming from a population where there's no relationship. And if they don't look to come from the same place, then we reject that hypothesis and conclude that there is a relationship. So these are the steps that go into a chi-square test. The first two, pretty straightforward because you are just formulating the hypothesis. Now, in step 3, you're going to determine what this distribution of test statistics looks like when the null is true. That is when there is no relationship in the population, right? You're just seeing what you're going to compare your table to. In step 4, you are deciding how sure you want to be that you're not making a mistake in your final decision, right? In step and then in step 5, you're calculating the test statistic for your table and comparing it to the distribution of tables where there is no relationship. And in step 6, you make a decision based on that comparison, right? So let's go step by step. Step 1 is state the null hypothesis. And the null hypothesis is always that there is no relationship in a chi-square test, is that there is no relationship between the two variables in the population. The key terms here is no relationship and in the population. All hypotheses are about the population. All right. So for our example of gender and attitudes towards or confidence in scientists, our hypothesis would be there is no relationship between confidence in the scientific community and gender in the population. Okay. The alternative hypothesis, step 2, is the opposite of that. We're saying that there is a relationship between confidence in the scientific community and gender in the population, right? But we're not going to test this one directly. We cannot test this one directly because we will never observe the population. We will test the null that there is no relationship. And if we can reject this one, then we're going to accept this one, the alternative. If we cannot reject this one, then we cannot accept that one. We can only accept that there is a relationship if we reject the null, that there is no relationship. This will become clear when we do an example. All right. In step 3, we are determining the sampling distribution of the test statistic when the null hypothesis is true, right? The null hypothesis is when the null is true, that is when there is no relationship, what does the distribution of chi-square statistics looks like? Right? Remember that in this step, we're looking at how the tables would be distributed or would look like if they were coming from a population where there's no relationship. We're doing this so that we can compare our own to that one, right? All right. So this step is about finding how the chi-square statistic would be distributed if it was coming from a population where there's no relationship, right? Or where the null is true. From statistical theory, we know how the chi-square statistic is distributed when the null is true. We know that it's a mathematical fact. Now, one complication here is that every table, depending on its size, follows a different distribution. Okay, so different sizes of tables have different degrees of freedom, and different degrees of freedom determine a different distribution. So in practical terms, to determine this distribution, we need to determine the table's degrees of freedom. All right, and for the degrees of freedom for a chi-square distribution for a contingency table, right, the degrees of freedom is given by a very, very simple formula. It's the number of columns minus 1 times the number of rows minus 1. Now, this is only the inside of the table. Don't count the totals. Do not count the totals. So if we go back to our example here, without counting the totals, how many columns do we have in this table? We have male and female, so that's 2 columns. And how many rows do we have without counting the totals? We have a great deal, only some, hardly any. We have 3 rows, 2 columns and 2 rows. If we go back to our little formula, we see, all right, so number of columns, that's 2 minus 1 times number of rows, that's 3 minus 1. So we have 2 degrees of freedom. 2 minus 1 is 1, 3 minus 1 is 2, 1 times 2 is 2. So we know that if we had in the population of a table of this size, right? If we sampled, if we took many samples for tables from this population where there's no relationship, right? All these, 2 by 3 tables, and we calculated chi-square statistics for each of these tables that came from a population where there's no relationship. We know that those chi-square statistics that we calculated would follow a chi-square distribution for a table of 2 degrees of freedom. Now, statisticians have calculated the probability that you will get each, any number in these distributions, and they are in these test statistic tables, right? This is a chi-square table that you have in front of you. And it says here for R is the degrees of freedom. Different textbooks use different letters, but anyway. So for this one, this is a table with 2 degrees of freedom, right? And we know these are chi-square statistics, and this is the probability, right, that you would get a test statistic as high as that, right? So for example, here, for this 2 degrees of freedom, right, there is here on top, you have 95% chance of getting chi-square statistics of 599 and lower, right? 95% chance. Or conversely, you have 5% chance of getting chi-square statistics higher than 5991. Let me say that again. From tables that come, right, from a population where there's no relationship with 2 degrees of freedom, and we calculate the chi-square statistics for all of them, you would have these tables, right? 95% of the time we'll have a chi-square statistic that is 5.99 or lower. And 5% of the time you get a chi-square statistic that was higher than 599, right? Again, sampling from a population where there's no relationship. So it would be kind of pretty rare to get a chi-square statistic higher than this, right? In a population where there's no relationship, it would be pretty rare to get one. It would be even more rare, right? To get a chi-square statistic of 9.2, right? You would get chi-square statistics of 9.2 or lower, of 9.21 and lower 99% of the time when sampling from a population where there's no relationship. You would only get chi-square statistics higher than 9.21, 1% of the time. 1 in 100 will probably give you a chi-square statistic higher than that, if you're sampling from a distribution where there's no, from a population when there's no relationship, right? So the chi-square statistic the distribution changes a little bit depending on the degrees of freedom, right? And when the degrees of freedom are, as you increase the degrees of freedom, of course, it's more likely that you would get chi-square statistics that are higher, right? A chi-square statistic of 6.6 for a table, for a 2x2 table that has 1 degree of freedom, right? There's 1% chance that you would get chi-square statistics higher than 6.63. Anyway, so what we're doing here is we're determining the distribution, right, with the degrees of freedom. And we right now know that our distribution for this example is 2 degrees of freedom, and these are the probabilities that you would get chi-square statistics as high as that. All right. In step 4, what you're doing is, all right, let's create a decision point here. Let's create a decision point that if we cross that number or that decision point, we're going to reject the null hypothesis. We're going to say that our population or that our sample did not come from a population where there's no relationship, right? Now, we can make a mistake, right? If we make that number too low, right? If we say, hey, if we choose a number that we can get 20% of the time or less, then that's going to be our decision rule. Then we're going to be wrong 20% of the time. That's pretty that's a pretty bad confidence, right? In social science and in the courts here in the United States, most people accept 5%. We're saying, okay, we want to make a mistake that we're saying that they're, rejecting the null 5% of the time or less. So here in step 4, we choose 5%, right? In social science, 5% or 1%. And this is by convention, by the way. Most people use 5% in social science. And we're going to look at get a critical value for that 5%. And like we said here, we're going to say, okay, so we're going to give ourselves a 5% chance of making a mistake, of incorrectly rejecting a null hypothesis. And what is the chi-square statistic associated with that probability? Well, for these degrees of freedom, that critical value is 5.99. And it says, well, this is how the tables look when there is when they're coming from a population where there's no relationship, right? And if our table has a chi-square statistic higher than this, right, then that means that, hey, it's not very likely that it came from this population, because we would get a chi-square statistic higher than this less than 5% of the time, right? So we are getting this critical value that is sort of like our decision rule. If we get a number higher than this, we're going to reject that our table came from a population where there's no relationship, because it's less than 5% chance that we would get it. But if we get a number from our table that is lower than this, there's more than 5% chance that we got it, that it came from a population, where there's no relationship. So that's what we do in step 4. And this will become more clear when we do an example. So in step 5, now that we know how the tables that come from a population that there's no relationship are distributed, now we get the chi-square statistic for our own table, so that we can compare it to those when the null is true. And we have to get a chi-square statistic for the whole table, right? So this is sort of the only involved math really for a chi-square test, because we need to calculate the chi-square statistic for each cell. And the chi-square statistic really is only a measure of how far our observed values are from what we would expect in a table where there is no relationship. So we need to compare the table that we got, the observed frequencies, not the percentages, the absolute frequencies, the observed ones, to what a table would look like if there was no relationship, right? Now, this table where there is no relationship is called the expected frequencies table. And we need to construct it, right? And the way we construct it is with this little formula. For each cell, we get the total in the column, right? For this 314, where did it come from? It came from the total in the column, 696, times the total in the row, which is 681, divided by the grand total, 1506. If we multiply the total in that column times the total in that row, divided by the total, overall total, we would get this 314.7. For this other one, female, a great deal, right? To get the expected frequency for that cell, we multiply the total in the column, 810, times the total in the row, 681, and we divide by the grand total, 1506. If we do that, this times this, divided by that, we get 366.3. And we get that for our entire table. Now notice that these numbers add up to the whole total in the column, and they add up to the total in the row, right? And it's the same as our observed. The totals in our observed, they're the same. The totals are the same, but this has changed. They have been distributed in there, right? And this is what the table would look like if there was absolutely no relationship between the two variables. If you get column percentages for this, you would see that they're identical. All right, so that's the expected frequencies table, right? Now we're going to calculate the chi-square statistic for each cell, which compares how much we're deviating from, or how much the observed values from the deviates from the expected. And to do that, we use this other little formula. So the chi-square value for each cell is determined by the observed, right, minus the expected, squared, and then divided by the expected again, right? So for this one, this 418.7, you would get by getting the observed, which is 351, minus the expected, minus 314.7, square that difference, and then divide by the expected again, by 314.7. If you do that, 351 minus 314 squared divided by 314.7, you will get 418. And you do that for every cell, right? So for example, for this one, male, hardly any, right? For this one, we would get the observed, which is 45, minus the expected, minus 46.2, square that difference, and then divide by 46.2. And we would get that. That's the chi-square for that little cell. Now, to get the chi-square statistic for the whole table, we would add the cell chi-square statistics, cell values, and we get a chi-square for our table of 14.68. 14.68. Right. Now remember, we're going to compare this chi-square statistic for our table with the chi-square statistics from tables that come from a population where there's no relationship, right? We already did that. I mean, we looked at them in the table, in the statistical table before. So to make a decision, we compare our test statistic to that critical value that we had that came from that table. If our own table is 1460, right, or 68, if it's higher than the critical value that we had, then we reject the null hypothesis. But if our chi-square statistic for our table, if this 16.6, whatever it was, if this 14.68 was lower than the critical value we got for a test, then we cannot reject the null hypothesis. Now, in this example, our chi-square for our table, 1468, is much higher than that critical value of 599. So we can confidently reject the null hypothesis. And if we do that, we can accept the alternative hypothesis. So if we reject the null hypothesis, and the null hypothesis that there's no relationship, then we can say that our table came from a population where there is a relationship. In other words, there is a relationship between confidence in the scientific community and gender in the population. Okay? Now, why is this? Let's look at this one more time. This is how a chi-square statistic is distributed, right? When the tables are coming from a population where there is no relationship. This is the value of the chi-square statistic, and this is the probability that you would get here is the probability that you get a number higher than that, right? The little one here. And up there is the probability you get a number equal or lower than that. In our case, for 2 degrees of freedom, right, we said there is 5% chance that we would get numbers higher than this. And remember that this is when the null is true, when there's no relationship. And there is 95% chance that we would get numbers of this or lower. Now, our number from our table is 14, right? It's 1468. It's much higher than this. The table ends at 9.2, and it says, hey, there is 1% chance that you will get a number higher than 9.2. 1% chance if the null was true, if this was coming from a population where there's no relationships. In our case, the 14.68, much higher than that. So it's much lower chance than 1%, much lower than 0.5%, that we would get a chi-square statistic that high if it was coming from a population where there's no relationship. So that's why we say, no, our table, there's no way, there's so little chance that our table came from a population where there's no relationship that we can reject confidently that null hypothesis and accept the alternative hypothesis. That's why. Now, a p-value, remember, the p-value is the probability that you would actually get a chi-square statistic of 14.68 in this case, if you were sampling from a population where there's no relationship. Now, as we saw on the table, the probability would be very, very, very small, much lower than 1%. Okay, this will become, again, clear in the example. Now, Google Sheets and Excel, they can help us do a chi-square test, right? We will not be able to do it all in one step, like other statistical software like SPSS would allow you to do. We need to do a couple more steps in Google Sheets, but it's completely doable. And Google Sheets has 3 different functions related to the chi-square test and the chi-square distribution. The first one is chi-dist, and this one will give us a probability of getting a test statistic as high as the one we put in Excel, given the degrees of freedom that we give it, right? So this one we will use to calculate a p-value. The chi-inverse function gives you a critical value of the chi-square distribution for the probability you give it and the degrees of freedom you give it. So this is the same as using a chi-square table. We won't need a table because we have this chi-inverse. Pretty much like the T-inverse that we use for like confidence intervals for a mean. And then we also have this chi-test function that actually gives us a p-value, just like this one, and conducts a whole chi-square test. And we only need to provide the observed frequencies and the expected frequencies for Excel or for Google Sheets to give us a complete p-value. So we're going to practice on this. To calculate a chi-square test, like I said, quickly, you can use this chi-test function, and you only need two pieces of information, the observed frequencies and the expected frequencies, right? And this chi-test will give you a p-value. It won't give you a chi-square statistic. It will give you the p-value, which is the probability that you would get a chi-square statistic as high as the one you did if the null is true. So if when you're using the chi-test function, if your p-value is lower than 5%, you reject the null.